So, and thank you, Carlos. So I'm going to give a bit of a deeper dive into Carlos's final slide there about some ideas for being able to make the main Chebi hierarchy something more of a community managed project. So on to the next slide. So just to kind of give some background, I use Chebi in quite a large number of projects. So, and some of these are quite major, US funded projects, either NIH funded projects. We rely heavily on Chebi and the gene ontology, the human phenotype ontology, the Alliance of Genome Resources, the Monarch Initiative. And with my Department of Energy funded hat, we're also heavily relying on Chebi in the National Microbiome Data Collaborative for making microbiome metabolomics data more fair. So I've long been a champion of Chebi, and I've kind of promoted its usage in a number of different projects. Moving on to the next slide, the reason why why we like Chebi so much is because, and why it's differentiated from other chemical databases, is because it provides a hierarchy. And we're not only interested in providing identifiers for individual chemical structures. As I mentioned in my previous talk, biologists like to group things together. We want to be able to find all genes that produce terpenoids, or find all data sets involving phenol exposure. All of the terms highlighted here in blue, actually they should be orange, correspond to class, what we might think of as grouping classes in Chebi. So these are things that don't have individual structures themselves, but group multiple different structures. So this could be things like amino acid as a grouping that groups multiple individual amino acids like L-lysine and so on. And Chebi is somewhat unique in doing this, although the situation is actually kind of quite nuanced, but is always been the main chemical ontology for use within OBO. But unfortunately, next slide, please. The classification part of Chebi has been a bit of a major problem. I think it's been neglected somewhat. I think, as we saw in the previous slides, the Chebi team have done a really excellent job in rebuilding their infrastructure for curating individual chemical structures. But this has come at the expense of the part of the ontology that is for classification. And I think there's a lot of kind of reasons for this that we could go into, but essentially it comes down to the fact that a decision was made a very long time ago about how to model certain things in Chebi, in particular how to model protonation states, and this has led to a huge amount of confusion in the community, and as a result, people essentially don't have the grouping classes that they need. This is a problem for the community, but it's also a problem for Chebi as well. Because it makes the ontology much, much harder to maintain. So if we go on to the next slide. So yeah, just a general kind of like outline. I'll kind of like talk a little bit about this problem, and then the solution that I'm proposing for this, which is a simplified version of the Chebi ontology, and then we'll move on to how we might go about deploying and implementing this. So if we, and also I won't spend too much time going over the problem itself, but if people are interested, there's a link here to a slide deck that shows in more detail some of the problems with the protonation states within Chebi. But moving on to the next slide, this is just a basic illustration of the problem. Biologists want to be able to describe the elements, for example, in a biochemical pathway, and they want to be able to pick the right Chebi ID to specify, for example, the output of the L-lysine biosynthesis pathway. This, as it turns out, is actually not completely straightforward. So next slide. The reason for this is that Chebi has what I call a forced specificity cross product, in that it does not give you a generic class for the L-lysine set of molecules. It forces you to choose a particular protonation state, and there is a somewhat unwritten convention about what identifier you should use. And there is a mapping file called the REA mapping file that tells you which of these correspond to the physiologically stable form. And about 50% of databases are using those identifiers, but another 50% of databases are using identifiers that correspond to the biologist friendly label, which might be L-lysine, but it may represent, the acid form of this. And this essentially doesn't really work up at the higher levels of the ontology. And if we go on to the next slide, it essentially means that when you have two Chebi terms that represent the canonical forms for two different amino acids, say L-glutamate and L-lysine, you might expect to be able to do what people do with ontologies, which is walk up the hierarchy and find the most recent common ancestor. And you might expect to find a term like amino acid as the common ancestor of glutamate and lysine. But in actual fact, if you use Chebi, because of the way the protonation states are modeled, the most recent common ancestor is polyatomic ion, which is a very, very high level and a particularly useful class. So it's got, and in addition, it's got all these other grouping classes that biologists don't really need. So on to the next slide. If you do want to get amino acid as a common ancestor, then you have to start introducing the conjugate base, conjugate acid edges, and this ends up just making everything like a lot more complicated. People who are using Chebi for AL reasoning have to use complicated AL patterns like GCIs in order to get the results that they need. And ultimately, this was never really driven by requirements in the first place. People just want a simpler ontology, such as, for example, on the next slide. Just to also mention that this is not just an issue for people who are using Chebi. This is an issue for the Chebi group and being able to maintain the ontology. So there's a number of issues in the tracker where we've used L reasoning to be able to determine that there are you have all these parallel branches for different protonation states in Chebi, and they're out of sync. And you can use L reasoning to try and keep them in sync, but the Chebi curation tool is very focused on individual chemical structures, so this makes it hard. So maybe just jump onto the slide after this. That's just illustrating that there's many kind of open issues about this. And Chebi is actually somewhat unique in providing this kind of structure. If we look at other classification systems like KEGG and Metapsych, and even the original version of Chebi that Michael Ashburn and Pankaj Jaiswal did in 2004, it didn't introduce this distinction, and this is nicely actually highlighted in the classifier paper as well. They also don't make this kind of distinction, and they essentially collapse the acid and anion forms. So moving on, we can see some examples of other chemical classification systems that don't do this, such as KEGG. And this table essentially kind of like illustrates the need for some kind of action on this soon, because what I'm starting to see is groups are moving away from using Chebi and starting to use simpler classification systems like KEGG that are essentially more biologist friendly, even despite the fact that these systems are not open. And I think this is a real shame. And I think I would like to see Chebi continue to be used as the main open ontology for chemical classification. But unless we make it more biologist friendly, I think people are just going to start migrating towards these other systems. So this isn't simply a matter of just being able to extract a subset from Chebi, because as we saw earlier, if we extract the subset, we don't get the grouping classes that we need. So it's actually necessary to do a more complex transformation to get a biologist-friendly Chebi, where you essentially do a subsetting and rewiring. And so we did in the Gene Ontology, we did a prototype of this, and we're calling just as a joke name at the moment, Chemessence. Our hope is that this gets taken over by Chebi, but I'll just walk through the procedure of how this was made on the next slide. So our first step is to take all of the terms within Chebi, whether they are leaf nodes or grouping classes, and essentially kind of like cluster them based on things like the Rhea Chemaxon pH 7.3 mapping table, the existing conjugate base acid relations in Chebi, and this needs to be supplemented with text mining because these are incomplete for things at the upper levels of the ontology. So as an example here are all the different forms of L-lysine. We take this, treat it as one cluster. On to the next slide. You can see we kind of group everything into these kind of clusters, and we essentially merge all of the relationships together. And this kind of like shows you the kind of like the parallel structure that you have within Chebi at the moment, where you've got all of the different protonated forms, each of their own kind of like parallel classification branches. So we group all of these into individual structures. And then next step, next slide, is that we identify a canonical or representative member from each cluster. So we follow groups like Rhea in taking the pH 7.3 form as the canonical one. That doesn't really make sense for the upper level one. So we've got kind of like heuristics for being able to take the representative for terms like amino acid. Next slide. Then we essentially kind of like bin all of the non-representative members. We obsolete them in this version of the ontology and keep only the representative members. And then we essentially rewire all of the relationships. So the rewiring doesn't make sense in terms of the semantics of the original Chebi, but it makes for this more intuitive structure here, where we're left with lysine and glutamate are subtypes of amino acid. Then on to the next slide. As a final step, we essentially relabel these. This is essentially being done by databases like Uniprot, as already. If you look at kind of like any of the Chebi terms within the Uniprot interface. So we basically rename L-lysinium 1+ as being L-lysine, and we treat it as the as if it is the canonical representative member. And then next slide. So when we apply this, you don't actually get such a large reduction in terms. You go from like 220,000 to 200,000. But in actual fact, the portion of Chebi that is used the most often is the most effective, So just taking, for example, random metabolomics data sets, about 40% of the terms are altered in some way. And you can see a screenshot of this simpler form on the left. I think this corresponds to something that a biologist will be much more comfortable with, and crucially, it is still fit for purpose. You can still use this for all the same applications that you used Chebi for before, including things like balancing chemical reactions and so on. So next slide. We can compare this with the existing Chebi. So these two amino acids all group under proteinogenic amino acid, rather than under a polyatomic ion. Next slide. And if you compare it with the full Chebi, with all of the different relationships, it's much simpler. You've got a much more intuitive classification structure. And next slide after that. We actually tried this using the kind of Go owl reasoning automated classification system. And we found this actually gives more meaningful classifications within Go for various reasons. So right now, for example, in Go, genes that are annotated to actin or rhodin biosynthesis are automatically grouped under dicarbolic acid biosynthesis, which is correct, but it's not as useful as some of the classifications you get when you use the simplified form. Suddenly all these genes are also grouped under polyketide biosynthesis, ketone biosynthesis. These are actually, I believe, chemically correct and much more useful, kind of like intuitive classifications. So next slide. So one problem with releasing this ontology into the wild and encouraging people to use this is it basically squats on existing Chebi IDs and subtly changes the semantics and rewires the edges. So this could potentially cause a lot of confusion in the community if it's broadly encouraged. One solution here would be to make different identifiers for these classes, which would be semantically compatible, but gets into kind of like territory where we're essentially perhaps confusing the community by making essentially a competitor to Chebi. So moving on to the next slide, what I think we should be doing is thinking about how we can, bring this into, into kind of Chebi more officially. And one way to do this is to essentially split how we govern and maintain Chebi. As we saw from Carlos's talk, they've done a fantastic job in building up the database infrastructure for managing individual leaf nodes or chemical structures. One thing that we could do is think about opening up the upper levels to the community, and instead of managing these in a relational database that only EBI people can access, is that we just manage these the same way we manage all of our other ontologies in OBO. We've got excellent tools for doing this, and excellent mechanisms for being able having people contribute via GitHub pull requests and so on. Onto the next slide and how that could look. So the basic data flow here is that the individual structures could be maintained in the EBI database. The classes, the grouping classes, could be maintained in GitHub using kind of standard tools. As far as the end users on the right, they don't see any difference. They, except for maybe some improved kind of classifications and improvements in maintenance of the top levels. Because essentially we could merge the two structures, both into a unified OWL file and into a unified database at EBI that could drive the Chebi API and the Chebi website. So that's the overall idea. I just want to thank the Chebi team and the Go team for their being very kind of like patient and understanding through this whole process. And thank you.